So it is my great pleasure to welcome Robert Dalang from École Polytechnique Générale de Lausanne, who is going to talk to us about polarity of points for systems of linear SPDEs in multiple dimensions.
So let me begin by thanking Anisotropic for the invitation to speak at this meeting, which I've been enjoying very much, including the excursion and the restaurant. Not only the science, but the atmosphere. It's not that I want to sound old, but when I arrived here, I realized that the first time I came to Cornell was 30 years ago. So maybe some people in this audience were not yet born. So it's a special pleasure to be here. I'm speaking on polarity of points for systems of linear stochastic partial differential equations in critical dimensions. This is based on joint work with Carl Mueller, who's here, of course, and Yimin Xiao, who's scientific committee, but unfortunately, I guess is not here. So here's an overview of my talk. So I'm going to give a brief introduction to this problem of polarity of points. It's a question that I've been working on, or at least on related questions, for a number of years, but probably that's not the case of everybody, so I'll see a little bit of introduction. I'm going to point out the existing results for Gaussian and non-Gaussian random fields, of which there are many, mainly in non-critical dimensions and also a certain amount in critical dimensions. I'll give a brief idea of what is the standard method, in some sense, for studying this issue of polarity in non-critical dimensions. And then the method that we're using, which is based on an idea of Dalang for handling critical dimensions. And he developed this idea in relation with fractional grounding motion. So maybe that's the one relation with similarity. Then I want to give the results that we've obtained for a fairly wide class of Gaussian processes, not all Gaussian processes, but many. And the particular interest is because of applications to systems of stochastic partial differential equations, mainly the heat and the wave equations. And for the moment it's linear because we want the solutions to be Gaussian. In principle, the method will apply also to other equations, but we study these for the moment. So the question of polarity of points. So I'm going to have a random field or stochastic process U, and so it has a parameter x which is k-dimensional. So k will always be the dimension of the parameter set, and its vector value, so it's valued in Rd. Okay, so there will always be a d and a k. D-dimensional value space and k-dimensional parameter space. And it will be continuous. So I fix a subset of the parameter space, typically a square or a wall or something like that. At least it should be compact with positive Lebesgue measure. And then I'm interested in the range of the process as the parameter varies in the set I. So this will be some random compact set. So the set of all u of x's as x varies in the set I, this gives me the image of the set I under the mapping u. And so the question is the following. You fix a particular point in the value space Rd, and the question is z hit by u? So that meaning, with positive probability, is there some x in the parameter set I where u of x is exactly equal to z? Okay, so does this happen with positive probability or not? And so polarity will be the situation where the probability that your range actually touches the point z is 0, so that's the situation where we say that z is polar to the process. And if the probability is positive, then it's non-polar. And you can sort of imagine that if the dimension is low, so if your value space is just R1, for example, then for fairly simple reasons you would hit individual points with positive probability. if the dimension d is large, then there's lots of room in RD, and maybe the range won't be big enough in some sense that it would hit an individual point. I guess the basic example is just standard Brownian motion. If you think of Brownian motion indexed by r plus, so one parameter with values in RD. Of course, if d is 1, then you do hit individual points. If d is 2 or more, then any fixed individual point will be hit with probability 0, so points will be folded. Yeah, so usually what happens is there's some critical value q, depending on k. So for a given k, there's some critical value q, such that in low dimensions, meaning smaller than q, points are not polar, so you do touch individual points with positive probability. And in higher dimensions, points are polar, so there's enough room that you will miss points. And what happens exactly at the critical value, d equals q of k, is usually harder to determine, and is not known in all cases. So usually the methods that work in the non-critical dimensions, unless they're very, very sharp, but typically are not sharp enough to handle without any additional work the critical dimension. And so this is what we're focusing on, is trying to understand what happens in the critical dimension. So let me give as very first example the random field called the Brownian sheet. So probably many people are familiar with this. But let me just remind you that this is, so a k parameter, here the parameter is actually an r plus k instead of being all of r k, but that's not essential. RD valued, and so if it's a Brownian sheet, it's because it's a centered continuous Gaussian random field. And so for each parameter x, we have the d components, w1 of x through wd of x. And since it's Gaussian, the process is determined by its covariance. And so the covariance of wi of x and wj of y is given by this formula. So delta ij is 1 or 0, depending on whether I is equal to j or not. And then here we have, so if you had k equals 1 and only one parameter, this would just be the covariance of Brownian motion. And then we multiply this for the different values of L from 1 to k. Okay, so yeah, k equals 1, this is just standard Brownian motion. And then for k bigger than 1, this is one of the multi-parameter extensions of Brownian motion, but not the only one. But it's one that has lots of helpful properties that maybe or one reason why it was more studied than some of the other extensions of Brownian motion, at least as most. I just thought I'd point out a few references of people who have studied this process over the years. And in the Bar's book, the Bar Krishnavizan's book, there's a chapter or so on the Brownian sheet, which is certainly a good source of reference for this properties of this process. And so what is the situation for this process? So this is, I think a definitive result obtained by the Bar Krishnavizan sheet. So for the k parameter RD valued Brownian sheet, fix a box, or a Cartesian product of intervals. And their statement is the following. So you have a subset A of the value space, subset A of RD. And you look at the W of I, so this is the image of the box under the mapping W, so the range of W as the parameter varies in the set I. Does this range intersect or meet the set A? Is the intersection non-empty, and what is the probability of this event? And so what they showed is that it's bounded above and below by these two quantities here, in which you see something here called capacity of A, dimension d minus 2k, which is appearing both on the left and on the right, and then what changes is just the constant c in minus. So up to constants, this quantity determines whether or not set is hit with probability, with positive probability or not. So I'm not going to define capacity because if you've seen it, you know it, and if you haven't seen it, the definition is a little bit too involved to be sort of captured in a few seconds. But the point is simply that it's a deterministic quantity that you compute, on the A is a deterministic set, you have some method for computing the capacity of A, here the Bessel-Reese capacity. So method that has nothing to do with randomness or the Brownian sheet, you determine this number, and then you have this case inequality. There were some related results appearing and so on. The only thing I want you to know about capacity is what I've written here. So we're interested in the case where A consists of a single point. So A is a set with a single point in it, which is Z. And the capacity of this set A with a single point in it is 1 or 0. And it's 1 if in low dimensions, if D is strictly less than 2K. And it's 0 if D is bigger than or equal to 2K. So if you study capacity, you can do this calculation, but that's the only really important thing for this talk. So if you think of a dimension D bigger than or equal to 2K, and you put A equals a singleton, that means here we have 0, so the probability is less than 0, so it's equal to 0. So that would be telling you that points are polar for all dimensions bigger than or equal to 2K, and in particular in the critical dimension D equals 2K. So here we're identifying the critical dimension for the bounding sheet, which is 2K. And points are polar in this critical dimension, and the proof is given by the inequalities of Cauchy on the sheet. So this is a very nice result, but it's somewhat specific to the bounding sheet. And we'd like to have results for a wider class of Gaussian processes. And so there's this class called Anisotropic Gaussian random fields, which I think was introduced by Guilherme, Capo, and Xiao. Two of those people are here in the audience. It's certainly worth mentioning. So this is a centered continuous Gaussian random field with IID components. So it's called a P of X, X and K. And let me consider the canonical metric associated with this Gaussian process. And so they called the process an anisotropic Gaussian random field if it satisfied two conditions. And so here are the two conditions. First of all, this canonical metric should not be degenerate. It should not take the value 0, bounded away from the origin, and it shouldn't be too large, at least when X is in a given box or rectangle. But the most important assumption is the one down here, which says the canonical metric should be bounded above and below up to constants by the sum that is here. So I sum over the components in the parameter space, xj minus yj to the power hj. So the hj is going to play the role of the Holder exponent if you move in direction j and keep the other components fixed. Okay? And this is the type of information that you often have for many Gaussian processes. You compute somehow the exponents hj, in the second moment. You compute this metric rather explicitly. And there is a second condition which plays a slightly less central role, because in certain cases you don't need it, but the conditional variance here of v1 of y given v1 of x. So v1 is just the first component. Be bounded below, and here we have the same type of expression with 2j, because we're taking the variance and not the L2 norm. But the hj's here are the same as in the other condition. Okay, so this is a class now of Gaussian random fields, and the result that they proved is the following. So in particular, you look at this quantity q, which is the sum of the inverses of the exponents hj. This might be an integer or might not, depending on the particular Gaussian process. But they prove these two inequalities here. So it looks sort of like the previous inequality. Again, in the middle, we have the probability that the random field V, as the parameter runs over I, meets a given set A in the value space. And so this is bounded above and below up to constants. And here we have what we had before, the capacity of A, with dimension d minus q, so q coming to this calculation. That's what we had in the result of the bar for the bounding sheet for this type of quantity. But here we don't have capacity anymore, but h stands for Hausdorff measure. Okay, so on the right-hand side, we have a slightly different quantity. Again, that's computed deterministically from the set A, has nothing to do with Gaussian processes. You can compute the right-hand side and the left-hand side, and you have this inequality. And to my knowledge, I think this is the best available inequality for a wide class of Gaussian processes. again, it's interesting to see what happens when we take A to be equal to a single point. So the capacity of a single point I mentioned before was 1 or 0. Here I've separated out the critical case where D is equal to Q, assuming that Q is an integer. The capacity is 1 for D less than Q, is 0 for D equals Q, and is 0 for D bigger than Q. Whereas the Hausdorff measure of a single point is actually infinity if D is less than Q, is 1 if D equals Q, and is 0 if D is bigger than Q. So there's a difference here, right, on this central line, but that difference is actually important because, you know, if D is strictly bigger than Q, this Hausdorff measure on the right is 0, so this probability is 0. That's saying you're not visiting points, the points are polar. If D is equal to Q, then here we simply have 1, essentially, a constant. And here we have 0. So in the critical dimension D equals Q, what this theorem is telling us is that the probability is between 0 and 1, which is not somehow a very informative statement. So, you know, this is a nice, very nice set of inequalities for the non-critical dimensions, but for the critical dimension somehow is not giving you very much information in terms of polarity of points. Okay, here's another example. So this is called Funaki's random string. And so here we have a process U which depends on t time and x is space, one-dimensional space. And so this is an RD valued random field which solves this stochastic heat equation. So here we have space-time white noise. Again, x is one-dimensional. There's an initial condition that's given. And so you can think of this for fixed time. You have something which varies in x. So this is the idea of a string. So it's parameterized by a one-dimensional object x. You have a string. It's random. It's RD valued. You have a parameter set which is essentially two-dimensional. So what is the situation? And so there's this result of Carl Mueller and Roger Tribe, where they identified the critical dimension for hitting points. So it's dimension 6. And they prove that points are polar in this critical dimension. Okay, so this is another situation where the idea of polarity, the issue of polarity has been determined in the critical dimension. So their proof is somewhat special. So it uses something called the stationary pin string. This was mentioned in a previous talk earlier this week. And scaling and time reversal. So this is a method of Paul Levy that Paul Levy, I guess, introduced for study of ground motion. But by replacing this object by a closely related object called the stationary pin string, they were able to use that same method of Paul Levy and handle the issue of polarity in the critical dimension 6. Unfortunately, so it's a clever method, but it doesn't apply to the wave equation. And it's not so robust because if you change the equation very, very slightly, so here in front of the noise there's, say, 1, constant 1. But you could imagine putting a deterministic function of time and x, of t and x. So deterministic, but say not constant. And then you can't use the method that is probability that was used by Carl and Roger Tribe. So it's a clever method, but it's not very robust, even under very small changes in the problem. It would not apply either to the wave equation. So this is a little bit special again, just maybe the result of the ground sheet is special. They did also treat the issue of multiple points, or at least double points, with the random string. There are a few results for non-Gaussian processes, and in particular for systems of one-dimensional nonlinear wave equations. So that's the equation I've written here. So second derivative in time, second derivative in x. And then here we have functions b and sigma, so an additive nonlinearity b, multiplicative nonlinearity sigma. These are Lipschitz functions. We're still space-time white noise, and x is still one-dimensional, so one-dimensional space. But now the solution is a non-Gaussian process, so we need somewhat different techniques to study this. But anyway, the result is the following. So a result of Eulalia, Rullard, and myself. The critical dimension is now dimension 4, and points are polar in this dimension. This again uses some rather specific properties. So for example, for the one-dimensional wave equation, we have K-Rolle's maximal inequality for multi-parameter Martin. So that's something that's used here in an important way. Since it's non-Gaussian, you know, for a Gaussian process, you access the density by the mean and the variance of covariance, but here we access it by analytic on calculus. So you know, this uses somewhat different techniques from the previous results on Gaussian process. But anyway, here we have the result for the critical dimension 4, and points are polar in this dimension. And then there are some results, but not quite as sharp, for other Gaussian, non-Gaussian processes. So in particular for nonlinear systems of stochastic PDEs. So here I consider a system of nonlinear heat equations. And so the spatial dimension, x can be in R1 or in Rk. When k is 1, you can use space-time white noise, so the covariance is here. Of course, when k is bigger than 1, the equation will not have a solution with space-time white noise, so we take a smoother noise, a spatially homogeneous noise, so white in time, and then here a Rees kernel, so x minus y to the power minus beta. The equation will have a solution if beta is between 0 and 2. And so we have this inequality, which sort of looks like the inequality of Garnier, Lacaux, and Xiao. So the probability that the process visits A is bounded above and below, and here we have capacity, and here we have Hausdorff measure. And if you look back to the previous result, there was D minus Q in that result, on the left and on the right. And here it's slightly less good because we have to add a small quantity eta. So you can fix eta positive as small as you want. And here we have D minus Q plus eta, and here we have D minus Q minus eta. So it's slightly less good than the result of Gaussian processes, but similar. Again, in the critical dimension here, which happens to be 4 plus 2k over 2 minus beta, so the beta being up here, when k is 1, space-time white noise corresponds to, k is 1, space-time white noise is when beta is 1, so then 4 plus 2, 6 over 1, so this is the dimension 6 that you and 5 have. But this is slightly even less informative than the result for the Gaussian process. This is for heat equations. For wave equations, at least in dimensions 1, 2, and 3, so nonlinear systems of wave equations, Marta Sanz and I have results of this kind, but with a slightly less good lower bound. Okay, so this is the situation for both Gaussian and non-Gaussian fields. And as you see, the critical case has only been answered for certain specific processes, and then for others, we don't have the answer for these results. So what I want to do is first explain briefly why the critical dimension, the non-critical dimensions are easier. So I want to show you why points are polar in dimensions that are strictly larger than the critical dimension. So this is a fairly simple argument that fits on this slide here that I'm going to show you. So I want to explain why standard Brownian motion with values in R3 does not hit points. Remember, the critical dimension for Brownian motion was 2. So 3 is bigger than 2, so we're in a non-critical dimension. And the method that's here is essentially, variations of this are essentially what is used for the other processes I've mentioned in non-critical dimensions. So here's the explanation. First of all, saying that all points are polar is slightly different from saying that almost all points are polar. So let's think for the moment about the issue of almost all points are polar. And it turns out that this is the same by a Fubini argument as saying the Lebesgue measure, so lambda d is for Lebesgue measure in dimension d, of the range is 0. So if I take the Lebesgue measure of the range and show that that's 0, in a Fubini type argument, this is essentially saying that almost all points are polar, and then a little bit of extra work will get you to all points are polar. So how would I prove that the Lebesgue measure of the range is 0? So I would cut the interval, here I've taken 1, 2, I could take any interval, but let's take 1, 2, into 2 to the 2n points, so these are tk is 1 plus k times 2 to the minus 2n. So I take a uniform partition of this interval 1 to 2. I want to cover the range, so to get an idea of the Lebesgue measure, I'm going to build a covering of the range. what is the simplest covering I can think of? Well, I just take B stands for ball, the ball, center, this is the center point. If I take one of the TKs, I take W of TK, so the value of W of TK, that will be the center of the ball. And I want to cover everything that comes from values of T that are not too far away from TK, so not more than one interval in this partition of interval 1, 2 that I created. So I take just the largest increment, Wt minus Wtk, as T ranges over this short interval E. Okay, so this will cover the range, right? Because I've taken these balls and the radius is sufficiently large to cover everything nearby the point Tk. And so the Lebesgue measure of this set, the image of W12, of 1, 2 under W, will be larger than the sum of the Lebesgue measure of these balls. So what is the Lebesgue measure of a ball? Well, in dimension d, it's just the radius of the ball to the power d times the constant. And what is the size of an increment if the parameter doesn't move very much, not more than 2 to the minus 2n? Well, the typical size is just 2 to the minus n. Maybe put an extra factor of n in here. So that to the power d. So now this doesn't depend on k, so I just count the number of terms, 2 to the 2n, times this value, 2 to the minus nd. That's this quantity here. And if d is 3 or more, right, remember we're in high dimensions. Of course, n to the d is going to infinity, but this exponential quantity is going to 0 much faster, so we're getting 0. And so just by covering W of 1, 2 with a uniform partition of the parameter space, we've shown that points, almost all points are polar in the critical dimension. Okay, in the non-critical dimensions, in high dimensions. So this is, a reasonably simple argument, and with slight variations, you often have a good estimate of the size of increments of a Gaussian process, even maybe a non-Gaussian process. So you can do this for the other processes that I mentioned. But of course, if d is exactly equal to 2, then you see that this argument just slightly fails. And so you need to do something a little bit different. Okay, so this is maybe a complex slide, but I think it shows the idea that with just a uniform partition of the parameter space, or an interval box in the parameter space, you can sort of handle the issue of polarity in high dimensions. So here's an idea for handling critical dimensions. So this comes from papers of Dalang in 1998. And so he's studying now a fractional rounding motion, so RG value. We call it X, so T is in RK, so K parameter, RG value. The variance of increments is written here, T to the minus S to the power 2 alpha. This today people would more use the letter H. And so here's the result that we proved. So yeah, there are certain constants and there's quantifiers, delta and k, with the following property. If you give R0 small enough and T0, you have this estimate here. And so let's take a few minutes to look at this inequality. So here we're looking at the largest increment for t not too far from t0, so not more than r units away. And so the inequality is the largest increment. So remember the typical size of an increment when t minus t0 is less than r would be about r to the power alpha. This would be the typical size. But here you're dividing by this extra quantity, which could be very large if r is very small. So this is saying that the probability that this increment is much smaller than you would expect, because you would expect r to the alpha. And here we have a quantity that is much smaller. It is bounded below by something that's reasonably large, right, if r0 is small. It's the probability that there exists an r in this range, such that this increment is much smaller than expected. You could not have this for every r, at least not for every small r. For example, just for rounding motion, there's something called slow points. But the slowest points are not quite as slow as this. So it's really, there exists R, there's a certain R in this range such that this increment is much smaller than you would expect. And this happens with high probability in this specific event. Okay, so this inequality is saying it's very likely that there will be some R, you don't know the value of R, such that increments of x in the ball centered at t0 of radius r are much smaller than is typical. Typical value would just be the numerator of your r to the alpha. Okay, so with this, if for a given point you have a high probability that this happens, probably many points will have this property. Of course, you have to make this precise, but this means that in some dimension, including the critical dimension, Dalang can use a non-uniform partition. So, the uniform partition was because you were saying the increment is of its typical size. And here he's saying there's certain intervals where the increment is smaller than you think. So you can use a longer interval. Hence, you'll need less interval. And so, when you have here the number of intervals that are coming into this length, you have fewer of them, you would have a slightly better estimate here on the right. Okay, so he can create a covering that uses a non-uniform partition, and so smaller balls. And this, with this, and a fair amount of work, of course, he shows that in the Hausdorff measure, the range is 0 in the critical dimension t, which is k over alpha, assuming that's an integer. Okay, so this is a very interesting idea, and we wanted to see if we could use this for the solutions of stochastic PDEs, for example. Of course, here he's studying fractional Brownian motion, but he says in his paper that if he's studying that process as opposed to, say, ordinary Brownian motion, it's because ordinary Brownian motion has so many extra properties that you tend to focus on, or to use those, and with this process you can't, and probably the method he's developing here can be extended to other processes, and we're realizing that that's the case. So let me just mention one feature that he uses for fractional Brownian motion, and that's this harmonizable representation. So this has also been mentioned in other talks. There are several representations of fractional Brownian motion, but he makes a strong use of this particular representation. And you can sort of wonder if you would have this kind of representation for essentially any Gaussian process that you would think of. And of course, we're thinking of stochastic partial differential equations. So if you have a linear stochastic partial differential equation, the solution is essentially of this form. So people who work on SPDEs will confirm this. You integrate like this. X minus y, w dot s y, y. So you have some sort of convolution where G is the fundamental solution of the equation you're considering, maybe the heat equation or the wave equation or something like that. So a solution of a linear SPDE typically looks like this, which a priori does not quite look like that. There's no convolution. So we like to have a method that would apply to this kind of process. And so, the first question is, could you expect to have such a representation for the types of processes we're thinking of, and not just for fractional Brownian motion? So as I said, there's many other representations of fractional Brownian motion. So here's another one. And then you have one-sided one also. Anyway, this already looks a little bit more like this, right? Here you have a term with t minus x, and here you have x and y. So you have some sort of convolution. Here you have a term that looks like a convolution. Well, there's this extra minus x to the power. But anyway, it looks more like what you would have for a stochastic partial differential equation. So you can wonder how it would go from one to the other, say from this one to that. And of course, people know how to do this, but here's one way. So let me give a name to the function here, x of t of x. And so y of t, if I think of white noise as a Schwartz distribution, so I'm just evaluating the Schwartz distribution on the function f of t. But of course, with Schwartz distributions, I can do Fourier transform. So, Now, this is a basic equality that you can check using elementary Fourier calculus. And you take the Fourier transform of W dot, and you take the Fourier transform, and here you have this check operation, which is sort of replacing the function f by f of x by f of minus x. And essentially, this is the inverse Fourier transform up to a constant. So if you put Fourier transform here and here, you have this equality. This is not specific to white noise. But what is specific is that the Fourier transform of white noise is again white noise. Okay? And so this Fourier transform you can simply compute. And you get this quantity. And you recognize here the real part with the cosine and the imaginary part with the sine. Okay, so by a Fourier transform argument, you can go rather quickly. I'm being a little bit uncareful with the issue of complex numbers, and I should be taking real parts. But the issue here is that with Fourier transform, I can go from a representation of this kind to a representation of that kind. And you can imagine then that you could do the same here, and that this, if you're lucky, will work. How does he use this harmonizable representation? So, the function I'm integrating here, say if I take this function here, then we call that capital F sub t. So we're integrating some function here against white noise. That's the function up here, say this function here in complex numbers. And so you're integrating over all of our k, but you could just as well integrate over a subset A of our k, and let A vary. And this will be a white noise in the sense that if you have disjoint sets A1 and A2, the integral over disjoint sets of white noise will be independent. So you're actually creating a white noise in this way. And the idea is that by choosing these sets to be certain intervals of this kind, remember we're interested in increments of the process. So we're interested in increments of this process here. It turns out when this function has a certain decay as psi goes to infinity, and if you're interested in increments of this order, say order 2 to the minus n times divided by beta, most of the increment of y will be given by this process where you take a to be this interval. Okay, so it will simply happen that maybe you can get a good estimate of this increment using just part of this integral and not the integral over all of our k. And so when you're using disjoint intervals, you have independent random variables. So you're sort of putting a lot of independence into your problem by using this process here. And so that's how he makes use of this harmonizable representation, sort of to create independence when you're studying increments over intervals of different sizes. Okay, so that's what we're going to want to have, why we want to have a representation of this kind for a wider class of Dalang complexes. So now what we've done is sort of isolated some properties that will allow us to get the same type of results that I want to obtain. So it won't be immediate. I'm going to state two assumptions. The first is starting to be stated here, that these are exactly what is needed, but we'll see that in the end that they are. So here's the assumption. So we have a process B, so some centered continuous RT-valued process. And the assumption is that there exists a Gaussian random field. So again, there's a subset A which will play the role of the A that was here, such that I have an RT-valued white noise when I fix X and let A vary. If I integrate over the whole space, I get back the process I started with. And when I have disjoint sets, these are independent random fields. Okay, so that's the one part of the assumption. And the second part is this one. And again, this one is maybe not so easy to see exactly what it's saying. But let's maybe look down at this last line. So I take here an interval from 0 to some number A0, and look at the increment. So this is saying that essentially this process, E of 0, A0, and X, is Lipschitz, right? The increments, the ultimum norm of the increments are bounded by this quantity, and there's exponent 1 here. this is a Lipschitz continuous process. The process V itself in general is not Lipschitz continuous if you think of Brownian motion or fractional Brownian motion. But we're sort of approximating increments of V by increments of this Lipschitz continuous process. And we're saying that they're bounded by this quantity here. So here again we have x minus y to the power 1, so this looks like Lipschitz. But here we have a constant in front, which is a to a certain exponent gamma j, and this is going to go to infinity as a goes to infinity. So the Lipschitz constants of the approximation are blowing up. And if we go from a to b, if b is infinity, then this would just be 0. That's some sort of, so this b with the minus 1 is some sort of normalization in how you're choosing to cut the set bar plus. But this is essentially saying that we're approximating a non-Lipschitz continuous process by Lipschitz continuous processes, and we're getting better and better approximations, but here there are certain constants that are blowing up. Of course, these constants are not completely, they're not arbitrary, they're very specific. And for example, if you know the canonical metric, like we know for many Gaussian processes, and say it has a bound of this kind, like we've seen for anisotropic Gaussian fields, and we call this quantity on the right delta of xy, then the alphas are the Holder exponents, and the gammas are related to the alphas by this equality, this formula. Okay, so if you know the alpha j's, which you know from any Gaussian processes, then you know what are the gamma j's here, which appear in this inequality. Okay? And with this assumption, then we can prove the same inequality that Dalang had for fractional Dalang. Okay, so the exact same type of inequality, the probability that there is an unusually small increment. So here, delta is the delta up here from the canonical metric. The y is less than this, such that delta of y x 0 is less than r. The typical increment would be of size r. And here we have a much smaller quantity, so we're saying with high probability, bounded below by this quantity, we have an unusually small increment. Okay, so the assumption might have looked a little strange, but it gives back the result that we had for fractional, that don't have for fractional Brownian motion, but here for essentially any Gaussian process satisfying our assumption 1. And then there's a second assumption, which is the following. So the first one states an upper bound on the canonical metric, and here we have the corresponding lower bound, so which is possibly different constant. And also we don't want the process to be degenerate, so it should not take down to 0, for example. But the important here is this second condition, which is a condition on covariances. So x prime is fixed, and I look at the covariance of vi of x prime with vi of y minus vi of y bar. So here I have an increment. And this covariance should be bounded by this expression. This looks precisely like the expressions we've had before, but the important thing is that delta j is strictly larger than alpha j. Okay, so before I had alpha j's here, and here I want a higher exponent. So I want the covariance to be smoother than what you would expect by looking at the sample patterns, for example. Now, if you just thinking of applying the Cauchy-Schwarz inequality to this left-hand side, you say the covariance is less than the product of the L2 norms. This is some fixed number, maybe. And then this is bounded by, we had the assumption that the canonical metric was bounded by this expression. But here there's alpha j's. Here I have delta j's, which are strictly larger. So the covariances are smoother than the sample. And many Gaussian processes actually have this property. If you think of Brownian motion, Holder 1/2 when it's epsilon, covariances might be limited. Okay, so this is something that occurs in many examples. And so with these two assumptions, here's our main abstract result. So we assume the two assumptions that I just mentioned. And in particular, that tells us that the canonical metric is bounded above and below by these two expressions, which were the type of expressions that were available for anisotropic constants. The critical dimension is this quantity, assuming it's an integer. Then we can essentially run through Talleyrand's argument, but replacing specific property of fractional grounding motion by the two assumptions I just mentioned, and obtain that points are polar in the critical dimension. Okay? So this is sort of an abstract result that applies in principle to many Gaussian processes. Of course, the issue is to what examples does it really apply? And so that's the last part of the talk. So, here's one typical situation. So linear systems of stochastic heat equations, first derivative in time, second derivative in space, space-time-wide noise, initial conditions 0 or anything else is not so important. And so in dimension 6, which we know from the work of Euler and Tribe to be the critical dimension, points are indeed polar. Okay, so of course we knew this from the work of Euler and Tribe, but it's sort of a fairly straightforward consequence of what we've done. And how do you check this? Well, you just check the two assumptions. And so I'll say how we get this harmonizable representation, but anyway, it's written here. So this is a process which in law has the same law as the solution to this stochastic equation. This representation actually already appeared in the paper of Dalang in 2012, which was studying different questions. But the point is that we just check the two assumptions. The method is robust. Remember, the Euler-Tribe result did not apply if you put a deterministic but non-constant function in front, but this method does apply. So it's sort of robust in that sense. How do you get this harmonic representation, harmonizable representation? Well, essentially, it's what I was telling you before. The basic idea is that the solution is given by this convolution formula that I've written on the whiteboard here. And then we do this argument of Fourier transform and just explicitly compute the space-time Fourier transform of the heat kernel. So we're more used to computing the spatial Fourier transform. We do the space-time Fourier transform, and out comes this function. And then you're in business to make the whole argument work. Of course, you have to check the assumptions. So you have to build this process which depends on this additional set A. And so here you have to integrate, instead of integrating over all of the parameter space here, the outside parameter space, so R times R, you just integrate over a particular subset. You have to choose which subset. But the solution to the heat equation, stochastic heat equation, is Holder 1/4 in time, Holder 1/2 in space. So this 1/4 and 1/2 that are appearing are not complete surprises. And so you look at the set of tau and psi, where this quantity is in a given set A, and then you get the type of inequality that was in my assumption 1. So remember, I was approximating the process I'm interested in by smoother processes. And here you get, so this A and B appear on the right. So a to the power 3 times the time increment, a to the power 1 times the space increment. Where did this 3 and 1 come from? Well, this was a relation I was mentioning before. We have Holder 1/4 in time. There's a missing input, so it should be 1/4 to the power minus 1, which is 4 minus 1 is 3. And here there should also be 1/2 to the power minus 1. 2 minus 1 is 1. Yeah, so we don't really guess these exponents, but they come from knowledge that we have of Holder continuity of the solution to the stochastic heat. And then you have to prove this inequality, right? These are the exponents you're aiming for, but you still have to prove this. And so that's some estimate of double integrals, right? Because you have to integrate over tau and psi. So, there's a little bit of calculus to do, some work to do, but you know what to aim for, and then you just have to show that that actually occurs. What about non-constant coefficients? Well, we have a similar harmonizable representation. It looks a little bit more messy. So here again we have the space-time Fourier transform of the fundamental solution to the heat equation that we saw before. And you convolve this with the space-time convolution involve this with the Fourier transform, space-time Fourier transform of the function sigma e. Now, of course, it should be that most of, you want to modify the equation by putting this sigma, but you don't want to modify it drastically. If your sigma is so irregular that the regularity of sigma is more irregular than the noise, somehow then this would not work. So sigma should not be too irregular. It can be non-constant. For example, its Fourier transform would be a measure with compact support. So that would be fine, and then the argument goes through this situation. What about higher spatial dimensions? So heat equation with spatial dimension k, this time with spatially homogeneous noise. Just to have existence of a solution, beta has to be in the range that's indicated here. But other than that, the equation is as before with the Laplacian here instead of second derivative in x. X is higher dimensional. The critical dimension is 4 plus 2k over 2 minus beta, and points are polar. But this is a corollary of the general result. You need the harmonizable representation, which is almost the same as before. So the first two factors are the same, and then because of the spatial correlation, there's an additional factor here. But you see that the harmonizable representation is not very different from what we had before. And now you have to check the assumptions. I haven't given a slide on that. Checking the assumption now is doing estimates on multiple integrals, so integrals of dimension 1 plus k, and you have to carry out the estimates. So there's some work to do, but it's just doing the appropriate calculations on these higher dimensions. What about wave equations? So here's a wave equation, spatial dimension 1, space-time white noise, initial position, initial velocity, one-dimensional space. Here d equals 4 is the critical dimension, so we knew that from the result of the Dalang itself. But again, we get this as a simple corollary. Checking the two assumptions and using this harmonizable representation, again, which is the space-time Fourier transform of the fundamental solution, and which you calculate explicitly and is written here. And this also appeared in the paper about the Capo. And then you do the calculations to check the two assumptions. And finally, the higher dimensional wave equation. So k bigger than 1, beta has to be in this range. Again, the Laplacian here, initial conditions. And so, there's this in red that I'll mention in a second, but the critical dimension is 2 times k plus 1 over 2 minus beta. Points are polar. And here we have a slight limitation, is that beta should not be smaller than 1. So beta has to be between 0 and 2 for the existence of a solution. So just to have existence of a random field solution. But our calculations so far work for beta strictly bigger than 1. And in part, this is related to the issue that covariances had to be sufficiently smooth. And the calculations are usually different for beta less than 1, so we did not do them. Or I did not succeed in doing them, it was more accurate. So for the moment, the theorem works for beta between 1 and 2. Again, take the abstract result, take the two assumptions. The harmonizable representation is essentially the same as for the one-dimensional wave equation. You see here there's an argument k, which is the next one k here. But the only difference is that there's this extra factor, as we saw for the higher dimensional heat equation. So let me just conclude by mentioning that these results are in a paper that's on the archive. And we're working on the issue of multiple points in critical dimension. So in principle, the same method will work. It's not quite completed, but for multiple points in critical dimension. And what we're also aiming for is to use these results for Gaussian processes to approximate solutions of nonlinear stochastic PDEs and handle the issue of clarity points. But that's not done. So thank you very much.
Thanks a lot, Robert, for this very interesting talk. Are there any questions or not?
Actually, this representation, this integral representation, is necessary or is necessary to see the assumption?
Yeah, so you're saying, could we do without these harmonizable representations? I mean, I think they're convenient because you have you have an integrand with a particular decay as psi goes to infinity, and having that decay explicitly is helpful. But my feeling is, if you wanted to cut up the space, so we're sort of chopping up the space of Fourier variables using this harmonizable representation, and sort of knowing the whole exponents gives us some idea of what we should be doing, and then we do it and it works. But I think you could sort of, here you have the ordinary variables, not the Fourier variables, but you could maybe figure out how to cut up 0t times rk in an appropriate way and get the same feature. But it just would not be as systematic. Certainly for the heat equation, we would be just doing something completely different, I believe, than for the wave equation. Whereas here we have sort of a single method that works almost identically for the two equations. The only difference appearing in the specific estimates that you have to do when you're evaluating the various integrals that you have to evaluate. But at least the method is the same for the false equations.
Actually, your general criteria are for one dimension, no? For the type of method is one dimension.
The time parameter. But there's also the spatial parameter. So the abstract result is for a parameter x of rk, so any k.
Any idea what will happen if you represent Laplace by fractional Laplace?
Let's see. I do have an idea, though I don't remember the results. So we would know the critical dimension. And we would have certain of the results that I mentioned of bounding below and above by capacity and Hausdorff measure. So a PhD student of mine has worked that out. And we would not yet have worked out the issue of polarity, but certainly the method would be applicable. And yeah, maybe that's something that we should do. So certainly the method will apply to that.
One of the byproducts of the probabilistic potential theory of this business always was not only that you could decide whether or not, say, points are polar, but in some sense quantitatively how polar they are. So what's the probability of coming close to a point? And it seems to me that you might have such estimates in the background at criticality. Is that right?
Oh, we don't have them, but you're saying we could
Might be able to produce such
might
estimates.
produce some estimates. So the probability of coming close to a given
I mean, those probability estimates have also other consequences in the analysis of
Okay, that's
processes in critical dimension.
that would be an interesting to look at. Yeah, so we don't have them.
But you know what I mean? For example, for bearing motion in two dimensions, the probability of coming with an epsilon on a plane is 1 over logarithm of the radius. So, and the belief is that all these problems should be like that.
Okay.
But is it?
Okay, we'll take a look.
Are there any other questions or remarks?
Are there any natural models when they are in the critical dimensions, the points are not forward?
So there are examples. Are they natural? Is maybe a different issue. So yeah. So Carl Mueller has described certain examples that maybe came from other people. But, yeah. So you have. I don't remember. So it's true that for the processes that we're used to, which have certain symmetry and so on, the critical dimension is typically the same as the higher dimensions. But yeah, you cannot guarantee that in advance. But the only examples that I'm aware of, the only example I'm aware of where in the critical dimension points are not polar, it's sort of an ad hoc construction that's designed to make this happen.
Any other questions, remarks? So let's think again.